Hi, Brad. Hi, Daniel.
Annoying. Alright, cool.
Chili mac.
Awesome. Okay, so here we go. Here's the plan. Today we're actually going to get through all sequences because it's just Louie and I. Awesome. Check it out. Here's the assignment. Yay. How many problems is that? 1, 2. Never mind. I'm not going to count for you. Alright. Yep, this is the whatever. Alright, chapter 8, sequences, L'Hopital, and improper integrals. We already covered part of this. So some of this is review, because I believe you ended with chapter 8 last year. Is what you ended with, or chapter 9? I don't know. Anyway, so part of this is review. Part of this is new. This is chapter 8. Welcome to BC. So sequences. A sequence, A of n, is a list of numbers written in an explicit order. For example, the sequence A of n, right, has A1, A2, A3, all the way to AN. A1 is the first term, A2 is the second, A3 is the third, etc., etc. The numbers are the terms of the sequence, and AN is the nth term of the sequence. Okay, cool. So it's just review. Any real valued function with domain, a subset. Wait, what? Any real valued function with domain, a subset of this.
Teachers like, oh, wait, what?
What was I trying to say? What was I trying to say? It's a good puzzle. Any real valued function with the domain is a subset of the set of positive integers. Wait. With domain, a set of the set of positive integers is considered a sequence. Okay. If the domain is finite, the sequence is a finite sequence. A sequence with a domain that is infinite is a infinite sequence. Oh, well, easy. Example 1. Find the first 4 terms and 100th term of the sequence with a specified nth term. Cool. So we're going to find the first 4 terms of a of n equals 3 minus 1 over n. And then we'll also find the 100th term, aka when n is 100, we'll find a 100, the 100th term. All right.
So we're plugging in 100.
Yep. Yeah, but first we got to find the first 4 terms. Can you see this?
So it would be like you plug in like 1 and then 2 and then 3 and then 4.
Exactly. So A1 is the first term, right? A1's the first term, so that's just going to be 3 minus 1 over 1, which is 2. A2 is the second term, so that's 3 minus 1 over 2, which is just 1.5. Or I guess we could say 5 over 2. Oh, you're right, 2.5, so it's 5 over 2, which is 2.5. Oh yeah, because we're minusing less every time. A3 is the third term, so it's going to be 3 minus 1 over 3, which is 5, let's see, 2 2/3? Yeah, 2 2/3. 6, so okay, that's 8 8/3. Cool. A4, plug it in, 3 minus 1/4, 2.75, or, 2 3/4. And then we need A100, so that's 3 minus 1 over 100.
So that's 3.9.
2.99.
Yeah, okay.
Chick-fil-A. Alright. Cool. That's pretty chillin'.
Cool.
The sequence in example 1 is defined explicitly because the formula is defined in terms of n. Another way to define, so the explicitly is the easy one because you can just skip right to finding the 100th term. If we were talking about recursive, man, this sucks because that means I'm going to have to find 1 through 99 terms. Shoot me. Another way to define a sequence is recursively by giving a formula for a of n relating to the previous term. So you have to find the previous term to find the current one. Find the first 4 terms and the 8th term recursively and the recursive defined sequence.
So we define 8 terms.
Well, unless we see a pattern. Trick play patterns.
Flex.
I need another word for trick play because now my students know it.
Flex.
Alright, so b1 equals 4. B of n equals b of n minus 1 plus 2. So I can start with b of 2.
This kind of reminds me of L'Hopital's rule. Or not L'Hopital's. What was the one that we did where it's like the differentiation?
Oh, tabular method.
No.
No, we want to be good. We want to be good.
Where it's like you find like the
Euler's method.
Is that Euler's? Oh yeah, it is Euler's.
Yeah, it's like linearization of a linearization of a linearization.
Yeah.
All right.
That's what this reminds me.
Sweet. Kind of. No, it is kind of. So b of n equals b of n minus 1. So it's 4 plus 2, so that's 6. B of 3, well, the previous one was 6 plus 2 is 8. B of 3, we have to find the first 4 terms. Oh, wait, we do have the first term already. B of 4 is 8 plus 2 equals 10, dot, 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 keeps going. What do you think it's going to be? B of 18. I'm sorry, B of 8.
B of 18.
B of 8. So 2 is 6, 3, 8, 10.
So probably 18.
Yep. How'd you get that?
Because you can see that the n times 2 plus 2.
6 is 12, 7 is 14, B of, wait.
Like if you look at
B of 5 is 12, 6 is 14, 7 is 16, B of 8 is 18. Yeah, you're adding 2 every time. So that's what I mean by, like, you can kind of see a pattern. But that's also why I had asked you for B of 8 instead of B of 100.
Well, like you can do that too. That would
Yeah,
be
you
100,
could.
That would be 100 or 202.
Basically. Yep.
Well, that's like what it would be. That's what the pattern is.
Would it be?
That's how I got B sub 8 and B sub 4. And
Oh yeah, you multiply by 2 and then add 2. Yep. Arithmetic sequences. A sequence A of n is arithmetic. What?
No, just saying that I remember this.
Sweet. If it can be written in the form A, comma, A plus D, comma, A plus 2D, comma, blah, 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 all the way to A plus n minus 1 times D.
I finished my chili mac.
Dude, what the hell? Okay. Fun fact.
What?
Fun fact, this arithmetic sequence, the thing I just boxed, I went through this with the 7th grader I tutored about like 3 weeks ago.
Thanks for making me feel bad.
Yep. I just wanted you to feel bad, especially since you shouted out about chili mac. This is the general form. A plus, don't worry, it's algebra 1. A plus n minus 1 times D. It's just a lot of people don't teach us algebra 1. For some constant D, literally you're just adding the same amount, so we could rewrite the former sequence as this arithmetic. I could have wrote it as A plus n minus 1 times D, where the D was 2, because that's a constant increase factor in our original that we started out with 2. So we could have rewrote the top one up here as 2 plus n minus 1 times 2. Think it'll still work. We'll plug in the first sequence.
So A is... why is A 2? Because it's like...
Wait, sorry, it should be 4.
Oh.
Yeah. I was thinking that, like, I see the pattern. Yeah. 4 plus n minus 1 times 2, because 2 is the change. So that's another way we could do it. Yep. Did I mess up?
No, I'm just...
So D is the common difference.
And how do you know that? How do you find it?
So D is the common difference here. You saw that we were adding 2 every time?
Yeah.
If I was subtracting 2, I would have put a negative 2 there. Huh?
But it's times.
Yeah, so this is n minus 1 times 2. So my first number, 1 minus 1 is 0.
Have to see, like, how it works out.
Yeah. It's actually super simple. You'll totally understand it. Each term in an arithmetic sequence can be obtained recursively from its preceding term by adding D. A of n equals A of n minus 1 plus D for all numbers greater than 2. Cool. Geometric, you're literally multiplying. Yay, A, comma, A times R, comma, A times R second, or just R squared. All the way to A times R to the n minus 1 for some non-zero R, because of course if R was 0, you're multiplying by 1 every time. R is called the common ratio, so if you're multiplying by 3 every time, your first number could be 1, then you have 3, and you multiply that by 3, that's 9. Well, here our A was 1, so this is the 1 times 3. Here's the 1 times our R squared, so that's 3 squared. And then I'll have 1 times 3 to the 3, well, because if you multiply by 9 by 3, it's 27. So that's basically what it's saying, where R is my 3, A was 1. Explicit rule, the nth term of the geometric sequence is A times R to n minus 1. Each term in a geometric sequence can be retained recursively from its preceding term by multiplying by R. Yay. Literally, if I want to find the fourth term, I just have to find the third term and multiply by 3. If I want to find the third term, I just find the second, multiply by 3. Like, you just go all the way down the line. Cool. Recursive, that's a computer science thing. Do I want to do an example with this one? Maybe.
It is.
Recursive? Yeah, until you find a base case. You're not. Okay.
We're just learning arrays. We learned arrays today. So like.
Okay. Cool. Cool. Alright, the sequence 1, -2, 4, -8, 16 is geometric. Find the following. A, the common ratio. What are we multiplying every time? Yes. So the common ratio is my r, so r is equal to -2. Alright, let's find the 8th term. So how do I find a of 8? The 8th term. Well, so if I could just use a of n, here's 8, that's equal to a of 7 times r. I also could do the nth term, sorry, let's see. Did I want to use that one? Oh, I could find the 7th, or I could do the explicit rule. The nth term of the geometric sequence is a of n times a times r n minus 1. So it's equal to a, our first term was 1, times the common ratio, which is -2, to the n minus 1. Here my n is 8, so -2 to the 7th. Maybe I should write that like this. 8 minus 1 is equal to -2 to the 7th, so that's just equal to -128. To the 5th is 32, times 2 is 64, so that's 2 to the 6th, 2 to the 7th, 64 times 2. Alright, recursive rules. So can we come up with a recursive rule?
We have to find 7.
For the nth term?
Yeah.
So the nth term of a geometric sequence is a of n equals a times r n minus 1. So for the nth term, a of n is equal to -2 a n minus 1. So that's a recursive one. Oh my gosh. I highlighted the wrong thing. I meant to do this one. I'm sorry.
Well, that should be to the power of n.
Let's do this one. So this is yeah, recursive. I was doing the explicit for the end. Well, no. Well, I don't know what I was doing. I was tripping earlier because I was like, where is everyone? Maybe it's the wrong day. Oh! Shalom.
Brad, Daniel's here.
I'm here.
Daniel's here.
I'm here.
Yeah, okay. So let's see. It's fine.
But yeah.
Explicit rule for the nth term.
Okay. Yeah.
Now you're good.
Thank you. Do you need to get a partner quiz?
Hell yeah, we do.
Do you need to Brad.
All right.
Oh, we haven't gotten through too far.
Oopsies.
Huh? Yeah,
Not
we've
too far yet.
done the 2 pages so far.
They're not good dairy intelligence. Dairy.
I love dairy.
That's my issue too. I do too, but I'm get really sick now. Now it's
Is your
just not
lactose
like
intolerant?
now it's not just like oh gurgle gurgle I feel horrible. It's like excruciating, like pain and throwing up all over someone's lawn yesterday because I clearly should not have drank that milkshake.
Can you catch them up on this? Quick.
Sure, I'll pause it. Example 4. The second and fifth terms of a geometric sequence are 6 and -48 respectively. Find the first term and common ratio and the explicit rule for the nth term.
Yeah, excuse me.
Okay, so in other words, a of 2 is equal to 6. A of 5 is equal to negative 48. Daniel, I was legit worried about you.
What?
Also, I found an email that apparently was addressed to you, but it was printed in the printer. The Berkeley School of Music audition or whatever. It was like the application. It was like to you. I don't know why it was printed.
Why was
The
it
faculty
printed?
workroom.
Oh, that's really strange.
It
I'll
is.
Take a look at that.
I don't know if you want me to grab it for you.
Maybe?
Did someone print it for you? Maybe college counseling.
Hopefully college counseling.
Anyway, so hopefully we're done writing this down. So, real quick, one thing you need to do.
Because you got my skin disease. I did. Yeah.
You need to memorize a of n equals a of 1 r n to the minus 1. So the first step is we need to find r. So
What is R?
the common ratio, what you're multiplying or dividing by every time. Since it's a geometric, so I'll go up to my previous example.
Oh, that makes
So
much sense.
with this guy, if I have a sequence 1, 3,
Yeah.
9, 27, well,
I
my
was
r
wondering how we got that.
my r is 3,
Yeah.
right? So this is clearly my, oops. So 3 is clearly my r. So I'm multiplying first by r to the 1, then r to the second, r to the third.
Great, that makes sense.
Cool. All right. So first step, we need to find r. So I know a of 5
Are we gonna learn
is equal
matrices
to-
again? Because I really hope we don't.
After we learn that for subject.
what?
Are we gonna relearn matrices in this chapter or are we not? Because I really don't want to.
I don't remember.
Do we cover matrices in BC?
Hmm?
Do we cover matrices in BC?
I don't remember. A of 5 equals, well, a of 2 times r to the 5 minus 2.
What is it?
Since it's a geometric, I'll multiply,
Oh, I see.
to get from r, the second term, to the fifth, I'm going to multiply by the ratio once to get to the third, multiply by it again to get to the fourth, multiply it again to get to the fifth. So I'm multiplying the ratio, like by the ratio 3 times to get to the fifth. So that's why I want it to be like r to the third. Yeah. So this is negative 48 equals 6 r to the third.
Question.
So negative 8 equals r to the third. So hold on, r equals negative 2. Check it out, our ratio is negative 2.
So let's say it's a to the 10 and a to the 8. It would be 10 minus 8. Is that a pattern? Or
If you had like,
a to the a 10, a 8, yeah, just two random numbers r. Then it would be 10 minus 8
Yep.
to find the ratio. Okay.
Mhm.
So that is.
because if we're going from the 8th to the 10th. What?
I just crashed so hard. I'm so tired. Oh, alright. Sorry.
Cool, alright. Next up, we need to find a1. Find the first term. So, because we wanted to find the first term, the common ratio, and the explicit rule for the nth term. So to find a of 1, I know a of n is equal to a of 1 times r to the n minus 2.
Shouldn't it be 1? Because you're finding a 1? Yeah.
Yeah. Sorry, it should just be 1.
No.
So I know a of 2 is 6. Might as well use that number. A of 2 equals a of 1 r 2 minus 1. So that's 6 equals a of 1 negative 2 to the first.
Right.
Divide by negative 2 on both sides. Negative 3 equals a1.
Or can you do it?
What?
Can't you just like
Divide the
think about
second.
it? Like it's
Yeah, that's fine. Whatever. Okay, third thing I need to do is find an explicit rule for the end term. Explicit rule.
I don't know what that is.
So it's the thing I highlighted. It's the thing I highlighted. Explicit is in terms of n. Recursives in terms of the previous. In terms of the previous term. Maybe I should write this out.
So it's a-n.
Explicit terms in terms of n, where recursive is in terms of the previous term.
So didn't we already write it?
Oops. A of n. Yeah. Basically, the thing I highlighted is what you need to memorize. That's the explicit one.
Oh.
So a of n
is
is equal to negative 3
We just should know it.
times negative 2 to the n minus 1.
But why do we have 3 in?
Because a1 is my...
Oh, I see.
This is negative 3. This r is negative 2. Awesome.
No.
Okay, just what I have to do. We can do some. We can keep going. How do you feel about this? Maybe I shouldn't ask how you feel. Okay, do we understand this?
Yeah.
No, you don't.
No, I think I will.
Okay.
I think I just need more practice. But
I understand it.
I think I'll get it. I think I can, if I sit down and try and like understand it, then I will be able to.
Okay.
Just
Limit, let L be a real number. The sequence A of n has a limit L as n approaches infinity. If given any positive number, epsilon, there's a positive number m such that for all numbers less than m, we have the absolute value of A of n minus L is less than epsilon. So we write limit of A of n as n approaches infinity equals L and say that the sequence converges to L. Sequence that do not have limits diverge. So converging versus diverging.
I don't get how there's a limit.
So if we say that as my sequence approaches a number, so for instance, the very first one we did, is there a limit to this one? So first term, second term, third term, fourth term, 100 term.
3.
3. You can see it gets closer and closer and closer and closer to 3. As n gets really, 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 really big, A of n is getting really, really, really close to 3. Right. So our limit's 3. So if I take the nth term and minus 3, take the absolute value, it's going to be a very, very, very small number. So the difference between them gets smaller and smaller. Louis!
Yeah, so no, I'm awake, but like...
No, you're not.
He's a sleepy boy.
I am awake.
So you could see that the first one was converging to a limit. You could see we got closer and closer and closer to 3. Yes. We were going towards 3. So that sequence definitely has a limit as n approaches infinity. If given a positive number epsilon, just it's a small positive number, there's a positive number m. So
what's an epsilon? Is that backwards e?
Yeah, that's what the epsilon is. So that means basically what we're saying is like, hey, guess what? The difference between the nth term and like the limit is actually gonna be negligible. Like it's not gonna matter. It's gonna be super small. We see we're getting closer and closer and converging.
So
this is
between the limit is not something to worry about. Huh?
What?
Like
I think you're gonna have to like go back and like approach this a different day to understand it because you look really tired.
Me?
Yeah.
Do I have to approach me for day?
Oh, no,
I definitely will have to come back to it. But
Yeah.
I'm trying to understand.
So let's see. What's your question? I don't want to spend too much time on this because the point of this was showing like, oh, okay. So as I have more and more and more and more and more and more terms, like an infinite number, the difference between the limit and my last term gets smaller, 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 till it's like actually not even important.
Oh, I see.
So it's saying like, oh, it gets so small.
That's a really crazy specific sign.
Huh?
That's a really crazy specific sign.
Sign?
Greek
For
letter.
epsilon.
Oh, epsilon.
Is that what
Yeah, that's very
epsilon
specific.
means?
No.
Yeah, epsilon is normally a very, very small change. That's what it normally corresponds to.
So it's less than a small change.
Yep. It's a minute, very, very tiny change. So the whole point of this little like box here is saying like, oh, if we see it's clearly approaching something, we have a limit. If it's not approaching, like it's diverging, we're not gonna have a limit. So for instance, this one, are we approaching anything? Yeah?
Yeah, we are approaching.
Yeah, what number?
None. No.
So if I said we're approaching infinity, it would like go up forever, except we're not. It's going positive, negative, positive, negative, positive, negative. It's actually, yeah, so it doesn't have a limit. It's not approaching anything. So that one doesn't, it diverges.
Like crazier and crazier.
So this is the difference between something like this. Wait, hold on. Something like this. Like that's a limit that's converging. Another way is like, oh, when I'm adding, let's see. So that first one we were talking about was like, it was going like, actually it's more like this. 1, 2, 3, so it was like 2, 2.5. So basically it almost looked like this type of graph where there's a horizontal asymptote at 3, but you can see we're clearly converging on it. Versus something that doesn't actually converge, it just gets bigger forever. Alright, so properties and limits, these are just review. We already actually covered this. This is one of the first things we reviewed in August? September. The sum rule, if you add two sums, you literally can add what their limits are.
The sum rule is my favorite.
Yeah, the difference rule, if you're subtracting the limit of an minus bn, cool, you can just subtract the limits. Product rule, guess what? Take the limit of both, just multiply the limits. Constant multiple rule, you can like pull that constant multiple out. I mean, we do this all the time. So I don't think...
I've never seen limit written as L.
What do you mean?
It says like L.
Oh, yeah, so that's the limit as n approaches infinity. So these are talking about, well, specifically about these, we're talking about sequences. So A of n, B of n are two different sequences.
So is L infinity in all these cases?
So all of these, if we actually have a limit, then we're actually going to be converging.
So if let's say it's limit of n as it approaches 1, L would be 1.
Depends. Is that what A of 1 equals?
A of 1 equals?
A1, yeah, the first term. Does the first term equal 1? Because this is a sequence, this is a sequence. A of n is a sequence. These are the limits of two different sequences.
As it approaches infinity?
As n approaches infinity. So what we're trying to do is take the limit of the very, very, very last term of our sequence.
What L means. Is L like the actual number
so,
that is the limit? Like
yes, it's the actual number.
N
So for the first example, L would be 3.
L is 3. Cool.
Yeah.
Okay.
L is the actual number.
That's the only question.
Okay. Determine the convergence or divergence of the sequence with a given m term. If the sequence converges, find its limit. Alright. So the way we do this, we say, okay, well, the limit as n approaches infinity of, let's see, 2n over n plus 3. This is going to equal what? As n goes into infinity?
2.
How do you know? How do you know?
Because if you look at the coefficients, the leading coefficient and the highest degree.
Yeah, basically. 2. So it's 2. It converges to 2. We're going to be approaching a number.
How do you know that it converges?
We are,
There's a limit.
yeah,
Oh, because
because we're actually approaching a number, not infinity.
and you can see that.
Next one, limit as n approaches infinity of -1 to the n times n plus 1 over n squared plus 2. Any clue how we could?
It's a row. Yeah.
Why could I do that? Do you know? Why did I say it goes to 0?
If you do a coefficient thing again, it's going to be 1 over infinity.
Basically. Yep. Dealing with the coefficients is basically like 1 over infinity, which goes to 0. So 0 times this other term is going to be 0. Whatever number this is times 0 just equals 0, so it converges. Looking at the exponents of infinity, cool. All right, a of n equals 1.2 to the n. So we have the limit as n approaches infinity. That's not m. So 1.2. What if I do this? So 12 over 10 instead to the n. So as we get bigger and bigger numbers, like 1.2 is the same thing as 12 over 10. So which means 12 is a bigger number. The top one's gonna get bigger and bigger faster. So we're approaching infinity. So it diverges. Because we're not actually like approaching a number. Cool. And the whole reason why it diverges is because this number is larger than 1.
Right, if it were
Because as we like 1 to the exponent, since we're larger than 1 to an exponent, it's going to grow. If it was less than 1, it would get smaller, smaller, smaller.
smaller, then we can converge.
Cool. Okay. So the sandwich theorem for sequences. That just sounds really tasty.
Sandwich. I didn't have lunch.
If the limit of... Well, are you okay?
Yeah, we just... Yeah, we'll wake up. Yeah, you have to, when it hits you like that, once you walk around...
It's because you have the itis. You gotta quit eating cheese.
What?
What? You have the itis.
Itis?
You don't know what it is.
Itis.
Never mind.
Oh, from the Boondocks?
That's not. Okay, if that's where you know. Never mind. Okay.
Wait, what's the itis?
That's where you know it from?
The Boondocks?
Okay.
Wait, if it's what I'm thinking of, it's for like when you eat and then you like pass out because you ate a lot? Yeah, I know that from the Boondocks. What do you know it from?
Life.
Oh, it's like an actual thing?
Yeah.
Oh, I thought that was just from the show. There's something they made up. Wait, what?
No.
It's like you eat a lot and then you like pass out. Like,
No, the Boondocks
because you're
take.
sleepy.
Never mind.
You watched the Boondocks?
That's not
Do you
where
watch
I
the
got it
Boondocks,
from.
though?
I watched it with my friends a little bit in college. Okay, cool. So
You don't like it?
we'll talk about this when I'm not screencasting.
What? I'm so confused.
The sandwich theorem, because I don't want to make Bradley sit through this.
Yeah, Brian
The
doesn't
sandwich
like
theorem
it.
for sequences.
What is it?
If the limit of my first sequence, if the like last term of one sequence is equal to L, that number, and the last sequence of L, which is another sequence, is equal.
I'm focused now. I'm good.
Alright, check it out. I have two different sequences. Here's one sequence. Here's another. What? They share the same limit. That means there's an integer, which is between the two last terms. Cool.
There's between the two.
Yeah, so what? Guys are we okay to learn right now?
Yeah, okay. I'm good. I just don't know what this means because it's all limit. So there's two limits. There's two functions with the same limit.
Yep.
There's two sequences.
So this means there has to be an integer for which that's between the two limits. So meaning all numbers bigger than that number.
All numbers bigger than that number.
Yeah. All numbers bigger than that integer n, where the sequence that's in the middle of A and C, of the sequence that's in the middle of the two previous sequences, also has a limit that's equal to L. It's hard to talk about this. It's hard to like. It's a lot of theory. It's a lot of theory. I worry about you sitting that way. Nope, I think you're gonna fall off because you're gonna pass out and sleep.
Yeah.
Yep.
No, that's why I'm sitting like this. So I don't fall asleep.
Okay.
And
Let's
doesn't
use the
fall.
let's use the sandwich theorem to show the sequence with the given n term converges and find its limit.
I just don't. Wait, sorry. Last thing. I just don't get why there needs to be a beat. There's two functions, and like one of them comes from.
Yeah.
What was that? Where's the X bar?
So like, there's two functions, and they both have a limit of 0. Then here's the other function.
Okay.
And they both.
That means there has to be a sequence that's between the top and bottom one. It's being bounded. It's being sandwiched in. Yep.
And that's all.
Exactly. That's all it's saying. Is there's a sequence that has to be between the top and the bottom one, and as you get more and more n, as you get more and more terms, as you approach infinity number of terms, it like squeezes it between. They approach the same limit. That's right. This is math.
Unnecessary.
Welcome. They make it super extra, and you're like, that's what you're trying to say.
That's what you're trying to say.
Okay,
So
so here.
Explain it like that.
You awake now?
So here, I'm literally going to be squishing cosine n over n. I'm squishing it between two terms. Well, I need to make sure that the terms on either side are always going to be, always going to be bounding in cosine n over n.
But those don't have the same limit. Cosine of n and n don't have the same limit.
That's cosine n over n.
Has the same limit as what?
Right, so I'm trying to find, so this right here is my B. This is my B. I need to find the A and the C to squish it, to sandwich it in. Here's one end of my sandwich. Here's one end of my sandwich, the A. Here's the other end of my sandwich, the C. This is my burger. Hold the cheese unless it's vegan. That's my B. So I need to
find the bread. We gotta get the sourdough.
Gotta find the bread. Gotta find the bread.
You gotta get that bread.
So
Bread
what's
time, my dudes. Sorry.
Are you flailing around?
Sorry. This is the only thing.
this is I like flail around all the time in class. People probably think I'm crazy.
I've never seen you flail.
I don't do it because I don't stand here and lecture for you guys.
Do you do that for other classes?
Yeah, it's the only class I sit in.
Really?
Yeah.
It's so weird. I can't imagine you up at the board teaching on the board.
Just because we've never seen it.
Yeah.
Yeah.
It's just different.
It's bizarre.
Okay.
There's 3 of you. I can be like, yo, stop. Take 2
Why
steps.
do you need to do that in
19 when I have 19 or 20 kids?
Yeah.
Yeah, I can't.
She wants to see
Did
all
Miss
their
Kasich do
beautiful
that?
faces.
Oh no, Miss Kasich sat at the stand at the
Okay. Right, I stand at the podium normally.
She walks around.
All right, so cosine of n has a minimum of, okay, -1. And it has a max of, okay, so I can bound it between -1 over n and just positive 1 over n. Because all of my n's are the same. So if at first, the first term, n is equal to 1. So I have -1 is less than cosine of 1, which is less than 1. So that's true. What about when n is 5? Right? -1/5 is less than or equal to cosine of 5 over 5, less than or equal to 1/5. So I'm like sandwiching it in because you know cosine goes like this.
Right.
Because the
Like
the over n guy, like that's the over n
making it
portion is
smaller.
making it smaller.
Right.
And then here's
but-
the positive 1 over n. Here's the negative 1 over n.
Well, couldn't you do like -2?
I'm sandwiching it in. Huh?
Couldn't you do like -2?
I could, but this is just why not? Why
But
not this
also,
one?
like, what about
Because this is the min and max of cosine.
what about plugging 0.5 in for n?
That doesn't make sense because n are integers because they correspond to my
Because it's a
term.
sequence.
Yes. Okay. Okay. So since the limit of n as it approaches infinity of -1 over n is 0, and the limit of n approaches infinity of 1 over n equals 0, guess what? The limit of cosine of n over n is equal to 0. It converges. Boom. Sandwich theorem. Done. That's it.
It's interesting.
You know what? Lucky for you, there's a screencast. 42-minute screencast.
Much of that is like just us talking about it.
I tried to reduce that.
You be done? No,
No,
for the day.
no.
No.
Shoot, we have 2 more minutes. I think we can do B, and then we'll only have like 1 page, and we can do
Wow,
8.2 next
this
time.
was scheduled for 2 days, right?
Yep.
Cool.
But I like trying to get ahead,
Rad.
especially because we missed Friday.
That's true.
All right, we're cool.
A crisp
B.
high five.
A of n equals sine squared over n over 2 to the n.
What?
So
Where's that page?
what? This is the same one.
Oh, shoot.
Part B. Yeah. Sneaky Pete. Here we go. So, huh?
You're so excited.
Who?
How we're not finding the page.
Yeah, it was great. It's the best thing I've seen all day.
Play.
Alright. What's another way to say trick play?
Ooh, yeah. Bamboozle. Plug and
Bamboozle. Wachoo. Abracadabra.
play. Gotcha.
I'm so confused with that.
Are you writing this down? Okay. So I
What's
need
the-
to.
what's the punked? Punked.
Yeah, okay. Nah.
Yeah, punked.
I need to sandwich this guy in. Where's my bread? Where's the
Where is that bread?
where's the
bread,
function that's underneath it? Where's the function that's above it?
Boy, bread.
That way I can
Bread.
squeeze it. I need to approach it from the top, approach
Right.
it from the bottom.
It's beef and moving bread time.
Dude, shut up. So I clearly am gonna have to have 2 to the n, something 2 to the n, because that guy won't go away, right? So that 2 to the n is the thing that's making sine go like approach.
Yeah. So it's always gonna be the same denominator.
Well, ideally.
Oh no. I'm gonna have I don't
Sine
even get
goes
why
from
it's
-1
2n.
to what?
I don't get why it's 2n at the bottom.
To the end, because there's 2 to the end on the bottom here.
But like
Because
you just said
because
that you put the same as the denominator every time.
I don't like
For our
making
class-
vague.
for our
I don't
class.
like making vague things like
Generally,
this.
yes.
I don't like
Generally,
making
yes.
rules that I don't know are 100% true.
But generally, yes, for our intents and purposes currently.
That's the easiest way to do it.
Cool.
Okay.
And why is it -1 and 1?
Well,
That's
sine
not
goes from a
positive.
-1 to a +1. I just want to be able to bound it by a function that I know is going to be less than it every time, and a function that I know is going to be greater than it every time. And guess what? If both of those go to 0, that means the one that was in the middle has to go to 0 as well.
I need to graph that.
Therefore, the limit as n approaches infinity. So guess what? As n goes to infinity, 1 over to the n goes to 0.
Oh.
What do you... What?
Oh.
Awesome. So we finished this page. I would really, let's see. So that's it for this lesson.
What's the purpose of sandwiching it? Like, why would we ever want to do
Because it's hard to take the limit of Sanskrit n over to the n. Because, like, I don't know, like, which thing, like, I don't know if it's going to converge or diverge.
Oh.
But here you can clearly, like, sandwich it in two things that are easy to tell the limit of. And since the one that's always above it goes to 0, and the one that's below it, that's always below it, goes to 0, like, the one that's in the middle has to go to 0 then.
Danny Hirsch is not going to be pleased when I'm